Okay, thank you, everyone. I know with all the details and challenges, we are now online, so we will move forward with the distinguished lecture for Srini. But before I say anything, I want to thank all the committee members who has really helped to put this together. And I want to give just a reminder for next week's seminar. We're going to go back to the format where we had two outstanding young faculty presenting. Our theme for next week is sustainability on energy and water. And the two speakers will be Kelsey Hadsell. She is right now an assistant professor at Vanderbilt, but will be moving to Princeton. And then the second speaker will be David Wasinger from Purdue. And it's also a time for me to congratulate Partha for being promoted to full, and he's going to be our moderator for that day. Now to the prime attraction for today. I will let Tim introduce Srini, but I want to just give a very quick intro for Tim Lewin. Professor Lewin is right now Regents Professor and David S. Lewis Jr. Chair in the School of Aerospace Engineering. He also has an appointment in the School of Mechanical Engineering. He also leads our Strategic Energy Institute. He is the executive director for that. Tim is known to everyone, so I'll keep it short. He's a member of National Academy. He's also a fellow of ASME, AIAA, and won several awards. And his research area is turbulent combustion. So with that, Tim, it's all yours.
Yeah, thank you, Devesh. And it's a real privilege for me to be able to introduce our distinguished speaker, who really needs no introduction. I've worked in the general area of fluid mechanics, particularly reacting flows, and so very closely followed Professor Sreenivasan's work, and so I'm delighted to have this opportunity. Just a couple words about our speaker. He is an international leader on turbulent flows. He's done seminal work across both experiments and theory and simulations, and he's one of those unique individuals who can really cross the boundaries of physics and engineering and math. He's a member of the National Academy of Sciences, a member of the National Academy of Engineering. He's a fellow of the American Academy of Arts and Sciences, a member of the Indian National Academy of Engineering, and just a host of other accolades. He's the past dean of the NYU Tandon School of Engineering and the past president of the Brooklyn Polytechnic, former director of the International Center for Theoretical Physics, and he is currently at NYU. He's a university professor and holds professorships in the Department of Physics, as well as in the Courant Institute of Mathematical Sciences. So with that, I will turn it over to Professor Sreenivasan. Thank you.
Yeah, thank you, Tim. Can you see my screen now if I close this?
Yeah, you need to share your screen, Srini.
Okay, let me share my window.
You went away.
Don't tell me we have the same problem again. Now, share. This works, right?
Yes, we can all see it, Srini. It's all yours.
Thank you. So I'm extremely perturbed by the fact that I couldn't show the slides. So I'm still agitated a little bit. Anyhow, this is my talk. I want to first congratulate this multi-university effort on this seminar series. I am very, very pleased to be a part of this. So congratulations to all the many universities that are involved. And thank you, Devesh, and thank you, Tim, for your inviting me and also for introducing me. In fact, you might see a slightly different version of this talk on the YouTube. So I want you to be aware that I've said this once before. So let me explain what my problem is. I'll start with the very basic thing of what the turbulence problem, so to speak, is. When the Reynolds number, which is the product of velocity, length, and divided by kinematic viscosity, is very large, generally there are many scales of motion that are excited in the flow. And this is turbulence, let's say, without being too pedantic about it. And the problem is to understand and also predict the motion of the entire range of these scales statistically. I want to emphasize it is statistical because, in fact, there is no other way to do this because there are so many scales of motion that are excited in the flow. And in fact, what I want to talk about is what's happened in the last 80 years or so of turbulence, but taking a slice through it. The statistical description was initially started by Kolmogorov. Actually, his first paper was in July 1941, so it is 80 years. And I want to take a part of that, and I want to review that first. And then I want to say how things have gone beyond that. So that's my goal. It shouldn't be very hard to follow, but I hope it will indeed be reasonable. So let's start with the so-called Zeroth Law of Turbulence. That's a name, actually, it turns out I had forgotten. I was the one who introduced it. Or the so-called Dissipative Anomaly, which is basically saying that turbulence is a super dissipator. But in quantitative terms, what I mean by that is you take the Navier-Stokes equations and convert it to an equation for the kinetic energy. It will have on the right-hand side a term which is the rate at which energy gets dissipated, and that is this quantity epsilon. This epsilon bar, which is the average of this epsilon, has this kind of behavior, which is viscosity times the squares of the gradients of the velocity in the flow. Now you might think that as the viscosity goes to zero, which is to say the Reynolds number goes to very large values and infinitely large, the energy dissipation would go to zero as well. But actually it doesn't. So here is what I said earlier, that is, as nu goes to zero, or the Reynolds number goes to infinity, one might expect that epsilon average goes to zero, but it remains a constant of the order unity in three-dimensional turbulence. Now it's called anomaly because this viscosity coefficient is a kind of symmetry breaking parameter. And when the symmetry breaking parameter goes to zero, you would think that the symmetry, which is the Euler symmetry, would be restored. That is, no dissipation would happen, but it doesn't. And this is not a new concept. G.I. Taylor simply stated it in his 1935 paper that the energy dissipation, when you normalize by the large scales in the flow, velocity q by L, which is making this dimensionless, call this d, he said that d is of order unity. It doesn't give you any idea of where it came from or what rationale he had, etc. But a little bit later, 1941, Kolmogorov made an attempt actually to show what this might, where this might originate. And basically, he said you take this d and take the limit of this as viscosity tends to zero, which is what we are saying will remain finite. And he wanted to show that the limit of d as nu tends to zero, which we might call d star, is of order unity. That's what I mean by turbulence being a super dissipator. Even when viscosity is practically zero, it still dissipates a large amount of energy, which is really related to how you inject it at the large scales. So that's the zeroth law. And in fact, I would say the concrete evidence for this came in this paper, which I happen to write. So on the right-hand side, on the horizontal axis is the Reynolds number, or you might imagine 1 over viscosity. So Reynolds number going larger and larger from left to right, or viscosity goes to smaller and smaller values, if you like. And this is this quantity d, normalized rate of energy dissipation. what you find is experimentally that there are at the low Reynolds number, or viscosity is large. There is a dependence on the Reynolds number, or viscosity, you might say, and then afterwards it becomes flat, independent of the Reynolds number, or independent of viscosity, if you like. And I also, by the way, this is the low Reynolds number limit, which you can work out exactly. And Doring and Fias had this kind of interpolation formula, which actually works pretty well for chosen constants A and B. And in fact, these are experimental data, but if you take the numerical data, computational data, DNS, which also I compiled in years later, you have the same behavior, initial dependence on Reynolds number, and thereafter things becoming flat. And now this has been shown to be true by a number of others, and I think we could take it as one of the truths, so to speak, in turbulence. The question is, why does this happen? If you look at the definition of epsilon, you can say that there is a viscosity times the square of the gradients, and the kind of simple explanation would be that when nu goes to 0, du dx squared, or the derivative squared, becomes very large, and therefore product of a very small quantity and product of a very large quantity remains to be of order unity. That means you have thin boundary layers, so to speak, formed all the time everywhere in the flow, but it is not really a theory of any sort. And so the best theoretical attempt, which still has some gaps, as I will tell you, is based on a conjecture that Ansager made in 1949. And these are the papers which has developed this conjecture. And I will say what the conjecture is as well. The conjecture is that this was made in 1949. It has two parts to it. One is that the dissipative weak Euler solutions, that is, you take Euler equations and you take the weak solutions of the Euler equations, and the dissipative solutions, the subset that really contribute to dissipation, have the Holder exponent less than 1/3, less than or equal to 1/3. This is what Ansager conjectured. And what does it mean? It means that if you take the velocity difference at position x plus r and the position x, the difference of that, take the absolute value if you like. This, instead of being proportional to r, which would be the case if the thing were a regular quantity, is going like r to the power h, where h is some number whose value it takes a number of values in a turbulent flow. And Ansager conjectured that the Euler solutions, weak Euler solutions, which are dissipative, have this Holder exponent h, which are less than or equal to 1/3. And you might say this has been shown to be true, that the dissipative weak Euler solutions have such Holder exponents. But what is missing is that these dissipative weak Euler solutions are responsible for the finiteness of dissipation for Navier-Stokes flows as viscosity tends to 0. There's a certain gap still that exists between what's been proved and what has not been proved, but that's the way it is for now. So that's the status of this zeroth law. But let's look at the next thing that Kolmogorov said. He said that, well, when the energy dissipation rate is finite and large in some ways, he said that if you take the velocity difference, which is what I showed you earlier, call that UR, take its variance, and this is just averages, and this variance has this particular form. The energy dissipation times R, which is the separation distance, to the power 2/3 times a function, a universal function of R over eta, where eta is the so-called Kolmogorov scale, which is nominally the smallest scale, dynamical scale in the flow. So that's really Kolmogov's form. And people know this generally better in the Fourier transform version of this, where the energy spectrum is epsilon to the power 2/3 k to the power minus 5/3 times a function that is a universal of k times eta. So this 5/3 law is something that everybody knows about, and that happens when the argument of this function f is very large, that is large wave numbers. This function goes to a constant, and then you have this so-called 5/3 law. This is something that everyone who knows any fluid dynamics knows, and even outside the fluid dynamics. And the other thing that is not always specified is that if you take a correlation length scale between 2 points in the flow separated by distance r here, now it has this form. It goes like r to the power 1/3 times another universal function of r or eta. Now, many years later, in physics, the so-called critical scaling came into being. Of course, it was known through the work of Landau in a certain way, certain simple way. But generally, in 1965, said if you have a critical phenomenon near the phase transition or something like that, if you write an expression for free energy in terms of this variable, which tells you how far you are from the critical point Tc, and a certain forcing variable here, you'll have a behavior on T, this thing here, 2 to the power minus alpha times G, which is a universal function of this again, and a length scale, which is of this form. Again, as T tends to 0, just grows without bound, just as here when R goes to 0. So you have this behavior, and this is universal for phenomena that are related to, let's say, equilibrium phase transitions. Now, this was therefore a forerunner for what happened in the critical phenomena. Of course, after that, renormalization came into being, and it became a big industry. And as you know, Ken Wilson got the Nobel Prize for that in 1979 or something like that. Now, this is fine as long as you take this velocity difference and you're interested in the variance. Kolmogov's formula is this. But you can also ask, what about when the velocity, when you have very large fluctuations in UR? UR here has a probability density. The variance only tells you what happens near the core of the probability density. But if you're interested in very large excursions or very large values, or extreme values and things like that, then of course you do not want to be content with the square of this variable, but you want to look at very high powers of UR or higher moments, and therefore you can sort of generalize what Kolmogov said to say that this delta UR, instead of squared, you take it to some power p. P may be very large, which means it will measure for you very large excursions, because these moments when p is very large come essentially from very large excursions. Or you can imagine p being very small, which is relating to extremely small values. It's sort of a microscope that you can apply at different levels in order to explore variations of this at different, you might say, extreme values. And if you sort of generalize this from Kolmogov, you said second moment goes like 2/3, fifth moment will go like p by 3. This is p by 3. And this would be the case when the argument of this function g is very large. So I basically wrote it as 1. And that is the case when r is very large compared to the dissipative scale or the small scale in the flow. And this is called the inertial range. Okay, so that is the extension of Kolmogov scaling. And we know nothing about this, whether this is true or not, except for the power 3 for which we know to be correct. Now, what's been established now, I think as a result of some 30, 40 years of work, is that this scaling here is not p by 3, but it goes like r to the power some zeta p, where this zeta p is not related to p in some simple way. If it were a linear function like here, if you sort of find the coefficient for 1p, you have solved the whole problem entirely. But if it is some nonlinear function of p, in a way whose functional form you do not know, then what it means is each moment will have to be somehow determined on its own merit. And that means you, for infinite order moments, which is what you need in order to describe the probability density, you have an infinite number of problems on your hand. In some sense, that is really the crux of the turbulence problem, but I've said it in a different way from what is said in the normal textbooks. And now this zeta p being some nonlinear function of p is this multiscaling or multifractality, etc. So I want to say what we know about this zeta p first, and then I want to show how maybe we have a certain simplicity that we can explore. So a few comments on the data which I am going to use in order to explore whether this is true or not. So I'll use direct numerical simulations in a periodic box, and that's a periodic box, and inside that is Professor P.K. Young, whom you know at Georgia Tech. I wrote, and these periodic boxes are the ones in which simulations have been done, and the largest periodic box in which PK has done simulations is 18432 cube, which is an extremely large box. Although I will not use such large boxes for our purpose, and the box is about 5 times the integral scale in the turbulent flow, and it is forced at low wave numbers, and different forcing schemes have been used, and basically there is no difference between different forcing schemes. Now, in order for you to understand how big these calculations are, the Reynolds number, the so-called microscale Reynolds number goes from 3 to 1300. So you have a factor of 1000, let's say, approximately. And the smaller Reynolds numbers have been really computed by Professor Donzis, who also has computed high Reynolds numbers. But I use data from these sources. And in order to compare for you with experiments, first I want to say that the range is adequate to address whether there are any finite Reynolds number effects, because I have variable Reynolds numbers which I can look at. And the high Reynolds numbers appear to be high enough for the property to saturate. So you should not be too worried as to what will happen if I had higher Reynolds number, etc. And in the experiment in Southern California, cooperative wind tunnel in 1966, Kistler and Rabolovich made these experiments before the wind tunnel was dismantled. It's a huge wind tunnel. As you can see, the test section was several meters in cross-section and 10 meters in length. And it was pressured, and the high Reynolds number data they had were R lambda 520. So you see that this has really gone way beyond this high level, high Reynolds number experiment. Another one that is of interest to us is the nice wind tunnel there is in Göttingen with the variable density flow. And it's about 1.5 meters in diameter, in cross-section length. And it operates sulfur hexafluoride at 15 atmospheres. It's a very complicated wind tunnel. And it can run up to Reynolds number 5000, but you can make measurements only up to about 1600 or so, which is comparable to the Reynolds number we have. So I'm sort of establishing all this, so you would really take these things seriously instead of saying, well, it's Reynolds numbers are low. Now let's look at the one part of the Kolmogorov formula, which is that the energy spectrum has a 5/3 factor here and a universal function when the spectrum is plotted in terms of this variable k eta. K is the wave number, eta is the dissipation scale. So what you find in the Monin and Eaglam's book, or some other places, for instance, is you plot k eta on this horizontal axis, and you collect data from many different flows that are shown here. You see different Reynolds numbers behave differently. As you go up in Reynolds number, this 5/3 part really begins to develop, becomes larger and larger, higher the Reynolds number. But there is this part here, which is the part connecting to arguments of k eta being larger, in this case of order unity. They sort of become universal. And this is to a first approximation appears to be true, although if you look at it carefully, considering how much you have squeezed the data on this logarithmic axis, in fact, there are differences from one flow to another, very significant, orders of magnitude in some cases. And I want to take you to the next slide, which actually shows what happens if you particularly focus on this at different Reynolds numbers, for example, going from 140 to 1300, where this is all supposed to collapse on each other. Well, it might appear to collapse on each other if you look at it at a coarse level, but it does not. In fact, there is a difference, and this is supposed to be the theoretical formula, and you can express this in these coordinates, for which, if there were universal behavior, this would first of all be one straight line, and you would have all these things collapse on each other. And that's not true. So in fact, this is easy to compute in some ways, but it shows that things are not as simple as one thought. And the way it will collapse is if you plot it not on k eta, but k eta times r lambda to the power minus half. So it's actually stretched. The important variable is not the Kolmogorov scale, but Kolmogorov scale, which is rendered smaller by this factor r lambda to the power half. Then you have an exponential behavior, and these exponents for high Reynolds number, as you can see, asymptote to a constant beyond a certain Reynolds number. And now, what gives you the indication that this is the right theory? And I will show you what the theory is on slide 14. But basically, I keep track of the slide number at the bottom right. So basically, we know that the Kolmogorov's theory would be okay if you normalize not using the Kolmogorov scale, but a much smaller scale than the Kolmogorov scale. That shows that dynamically there are scales that are smaller than the Kolmogorov scale, and they become more and more visible the higher the Reynolds number. So that is the lesson from there. The next thing is, of course, you want to look at the moments, high order moments of this velocity difference. And I want to first of all know whether the power law, as Kolmogorov said, if you do this, he said r to the power something, and what those somethings are. So that is the purpose in this slide. So what is plotted here is r on this axis. This is distance, separation distance between the 2 points, and normalized by the Kolmogorov scale. And on the vertical axis is this quantity here in logarithmic units. So if you have a power law, you would see that as a straight line. If you go for r or eta beyond, let's say 20 or something like that, there's a nice straight line up to about there. And in fact, these are different situations and they plot on each other. And here is another case for a different moment, etc. So in fact, this exercise says that there are power laws. And I want to be a little bit more stringent by taking the local slope of the data here, the logarithmic slope, and plot it as a function of r or eta, as shown here. This is the slope on this axis, and r or eta here. And these are for 3 different Reynolds numbers. You see, for if there were a perfect power law, then the slope would be constant in a certain range. And for 400, it is almost showing that behavior. For 650, it is getting there. For 1300, it has at least this much range that is true. And this trend seems to be clear that the higher the Reynolds number, you would get a region of constant slope. And that's what really happens if you go to much higher Reynolds numbers. But the quality does not change from here on. So now what in this plot we have done is, this is the moment order P. So you do this exercise, the one that I showed you before. I showed you for 2 different numbers P, different values of P. And you can do this for any numbers of P that you are interested in, and prepare log-log plots, get the local slopes, and get the value of those exponents. Okay, so what is plotted here is those values of the exponents on the vertical axis and the moment order on this horizontal axis. And if Kolmogorov were right, that would be the straight line behavior. And in fact, it seems to be pretty nearly true for very low order moments, that is near the variance and things like that. But if you go to high order moments, that is not true. These are various theories which I will not dwell on. And so it sort of seems to go like that, different from here in some nonlinear fashion, in contrast to this linear behavior, which is what Kolmogorov's extension of the Kolmogorov's theory would tell you. And now what is also interesting is that this is for longitudinal velocity differences. If I take the transverse, that is velocity differences across a distance perpendicular to the direction of the velocity, and you do the same exercise, they sort of behave like this. They not only depart from this, but they saturate for large orders of P. And this number to which it saturates is around 2. And this may be related to the vortex structures in the flow and so on, but I will not dwell on that too much. But now I want to explain what is the importance of this in the first place. We already mentioned that if you want to look at extreme events, this is the way to do it, one way to do it, let's say. But I want to say what the importance of this saturation is. So I'm doing this, right? This is what I'm doing, delta R U to the power P, average value. And I put it here normalized way. This is large scale velocity to the power P, R or large scale to the power zeta P. And this zeta P is what is plotted here. Now, you instead of, see, if you have a stochastic variable, you can take either the root mean square value as its representation. That would be true if the distribution were Gaussian. But if the distribution has large tails, as in turbulence, then of course, for different orders, you will have different quantities. If you take delta R U to the power P to the power 1 over P, that is not the same for each values of P. And that is what, in fact, we showed already here. So if you put it in this fashion, then a little bit of this manipulation tells you that the exponent is zeta P over P, and P is a linear relation, and zeta P is saturating. So this quantity goes to 0 for large P. Therefore, simply that this one will be unity. And therefore, delta R U to the power P, 1 over P, is of the order U naught itself. That is to say, the extreme fluctuations in the flow are of the order of large-scale velocity itself. So you think that the turbulence sort of, fluctuates a little bit over different scales, and over each small scale, the fluctuation is simply very small, you might think. But in fact, this is saying that there are, in fact, positions or places in the flow where the fluctuations are of the order of the large-scale velocity itself. That is, if you have a jet, for instance, the largest velocity you can have in the jet is between what you go at the center line at the exit of the nozzle and the ambient. So that is the largest velocity possible. So if you stick your probe in there and wait long enough, you will in fact see fluctuations, even on very small scales, which are of the order of this largest velocity. And this is fundamental as well, for instance, in some ways, but also practical. So I think that is what this is saying. It says that the flow at some point becomes shock-like and locally, across which the jump in velocity is of the order, even on smallest distances, is of the order of the largest velocity in the flow. And this is possible, one thinks, because in nonlinearity, as we always know, steepens everything, steepens velocity fluctuations. But in turbulence, it is there is pressure as well. The pressure tries to balance this effect of the steepening of the nonlinear terms. But what happens is, if the fluctuations are very large, the nonlinear steepening effect sort of wins over the pressure, and the pressure essentially becomes irrelevant for such large fluctuations. So this is the nonlinear steepening about which you know. This happens in many contexts in compressible flows, for instance. As time goes, these things become steeper and steeper. So let me just say that for the having seen this for transverse, and having seen that the longitudinal ones do not saturate up to this order moment, I asked Karthik Iyer, who was working with me at the time, to push this, even though we may not believe those numbers very much because of convergence issues and so on. But he pushed it, me being responsible for showing this data. In fact, they too seem to saturate for very large order moments. But whether it is true or not, I do not know at the moment, but it looks like a possible thing. Now, this is also the case for passive scalars, that is temperature, for instance, in a slightly heated flow, where they saturate much sooner in terms of the order of the moment, and they saturate to a very small value. And we know this very well, understand this pretty well, I think. And this is what happens in the Burger's equation, where shocks are formed, and in the Kraichnan model for the passive scalar as well. So I think that is an important factor. And now this is slide 14, where I'm supposed to show you the theory for where we got, instead of the Kolmogorov scale to the power, Kolmogorov scale times Reynolds number to the power minus half. So you're dealing with fluctuating quantities like this, which are really many, many hundreds and sometimes many times thousands over of the mean values. So it is clear that mean values will not tell you anything about such quantities, because the mean value will be somewhere near the noise level. And if you want higher and higher order moments, you want these peaks are the ones that contribute to it. And if you want to know what the probability density is, you need to go to higher and higher order moments. Now, the basic point is that you have a scaling region where there is a power law for this kind of quantity for R. And then you have a region which is really viscous dominated, which is regular. So you sort of try to match the two of them. And you match them at a scale eta, where the Reynolds number based on this velocity difference is unity. So the smallest scale in the flow is of the order of viscosity divided by the velocity difference across that scale. Now that means you can, this is in fact the only relation I'm going to use in all this, but maybe I'll skip in view of the time and simply say that for different order moments, you will have different values of eta, and the one that you're interested theoretically is the one for the largest order moment, or the moment order increases to infinity. So if I call this eta 2n, I'm interested in the behavior of eta 2n as n tends to infinity. So the upshot of this exercise is that that scale divided by this length scale, big scale in the flow, is Reynolds number to the power 1 over zeta 2n minus zeta 2n plus 1 minus 1. if zeta 2n saturates, then zeta 2n is the same as zeta 2n plus 1. So I will have this equals that, canceling each other. I'll have Reynolds number to the power minus 1. So the smallest scale of interest as n goes to infinity is not not Reynolds number to the power minus 3/4, which is what you find in all the textbooks. According to this theory, it is Reynolds number to the power minus 1, which is the Kolmogorov scale times Reynolds number to the power minus half, or Reynolds number to the or minus quarter, which is what I showed earlier. So what it means is the higher and higher the Reynolds number you go, the small scales get more and more populated, and theoretically they will truncate, not at Kolmogorov scale, but at a much smaller scale than that. And if you are particularly interested in singular behaviors and understanding things like extreme events and all that, this is where you really have to look. Okay, so that is what we know, and I want to summarize for you what we know so far, and that is, Devesh, how much time do I have? We started a little late, but tell me how much time I can go up to.
You still have about 20 minutes, 25, Srini.
Oh, great. Okay.
Yeah.
So what we know now is that we know that turbulence has anomalous scaling, that is to say not equals p by 3. So even if some caveats are violated modestly, this anomalous behavior has been demonstrated many times. And the new aspects that have emerged from what I showed is that different components scale differently, they saturate to different levels, and this makes the meaning of universality quite different and quite restricted in some ways. And to me, it looks like the era of Kolmogorov's universal scaling is over, even though it still provides a lot of inspiration to many of the things we do. So now, what is it that I am proposing or looking at in a slightly different way? This is the Eulerian loops in 3D turbulence and the circulation around them, which was the second part of the title of my talk. So you imagine you have a turbulent flow and you draw an Eulerian loop, that is a loop that sits in the flow, and you compute the circulation around it. Now you take another loop of different area and you compute the circulation around it. It'll of course be a different number, and so the circulation is is again a stochastic variable because the velocity field is stochastic, and you want to know what its properties are, and in particular if it has any simplicity in relation to the velocity differences that I just talked about. Now, so that's what I have already said. So area, arbitrary shape, contour C, and circulation around it is just the line integral, and by Stokes' theorem it is equal to the area integral of the normal velocity in this loop. So if this is a square or a circle, the area is completely specified by a linear dimension, but otherwise I will just have to talk about the area. If it is a square or a circle, I will just have this relation r proportional to square root of that. Now, of course, everybody knows fluid dynamics, circulation is very important. You may know this is also connecting back to Georgia. When Jimmy Carter became the president, and as you know, he was a farmer, and there were crop dusting that had to go on using planes, and he brought with him, when he came to Washington, D.C., a NASA engineer who wanted to understand the effect of these wingtip vortices on crop dusting. So they made a lot of experimentation using colored smoke and everything, and you can see this beautiful vortex at the tip of this wing. This vortex is even bigger than the aircraft itself. And of course, this is the most familiar form of the circulation, familiar example. Also, you know that if you have a circular cylinder, like here you have these vortices, well-defined circulation. When, of course, you push the Reynolds number very high, in a flow like this, for instance, it becomes turbulent, But imagine that you can still take circulation around a loop, and that loop may or may not represent a physical structure, but it will have some interesting properties to consider. So the nice thing about it is Migdal has a theory that came from quantum gravity, which I will not describe. And it has, he proposed one very important rule. And that is, if you take the circulation around a loop like this, as long as the area of the loop is the same, the circulation statistical properties are also the same. That's a very interesting thing. If I take a square or a rectangle which has the same area, circumscribing the same area, but aspect ratio very large, then it somehow seems to be, if the area rule is the same, then the statistical properties say something very deep about turbulence. Now, what we did was, you take this high Reynolds number flow, and you compute the circulation around circulation gamma around a contour C of a given area, and you get the circulation around it, and you plot the probability density, and then you change the loop, and you repeat the same thing and plot the probability density again. And if the area rule were true, then the probability density function must be a unique thing. In fact, if you do this for loops which is this size for different values of L1 and L2, this is what you find. You actually find the probability density essentially following, essentially having the same behavior for all L1 and L2. This here is the Gaussian random variable, which has a very different behavior. It's a parabola compared to this. Now, of course, again, I am ignoring these last points, which have whose sample size is very small, 2 times 10 power minus 7% of the sample. So in fact, I ignore that. So if I ignore that, that's what I have. You might say, well, I'm squeezing things over log scale again, and if I really expand it, will they look the same or not? In fact, I will show you that in a slightly different way. Then another part of the theory of Migdal was that the behavior will be like exponential modulated by a square root of gamma, essentially exponential for very large values of gamma. So in this red line that is plotted here is the theory. So that seems to work pretty well to a first approximation. But you really want to put because it seems to work so well, maybe you want to put it to a higher scrutiny. And that's what I will do now. And again, using the Reynolds number from these many boxes. And you should not worry about whether the statistical convergence of the data happens or not. This has been looked at many times. And I wouldn't want you to waste your time thinking about that part. These are the references where it's been looked at. I want to call attention to Iyer, who is now a professor in Michigan Tech, and of course, Georgia Tech's P.K. Young. Bharadwaj is one of my graduate students now. Now, what Migdal Polyakov pointed out, another well-known string theorist, was that if you look at the second moment of the circulation, you can write it as this double integral. And in fact, it will have some dependence with a power law exponent on the length of on the characteristic dimension of the loop, but it will have a quantity in front which will actually depend on the shape of the contour. So that's what he said. And so you really, in fact, area law cannot work, but I will show you what the data show in the next thing. Now, here, let's look at this inset first. What is plotted here is the circulation to the power m divided by 1 over m for a rectangle of arbitrary aspect ratio divided by the one for the square, and this parameter here is the one that characterizes the aspect ratio. So L1 and L2 are the two dimensions, and this ratio here is 4 for a square, like here. And if the rectangle has this aspect ratio, approximately 4.6 or something like that, approximately 4, that has a value. This has a value 4.6. So in fact, I'm going to go from rectangles, from squares like this to rectangles like this. And of course, rectangles which are stretched out in the horizontal dimensions are the same as these because of the isotropy in the problem. And I plotted here as a function of that parameter 4 to 4.6, which is going from something like this to something like that here. Different moments, for different moments, this ratio 2, 4, 6, 8, 10, and 12. So in fact, the top ones are for 2. Even if you go from this to this, as I said, going from here to here, the variation, there is a variation, it's not constant. So technically speaking, area rule is not correct. But on the other hand, the variation is so small. You see, it's only 2% or so different from here to here, which means that area rule can sort of be used as a practical thing, for instance, essentially. Now, if I go to very high order moments, like 12, it becomes a little bit worse, but it only is still about 5% off from here. And what you also find is, if you go to the full picture now, which extends theoretically from 4 to 11, this really, you'll have to imagine, is completely stretched out in one direction or the other. What happens is that the difference in going from 2 to 4 is larger than going from 4 to 6, 6 to 8, 8 to 10, and 8 to 12. In other words, as you go to higher and higher order moments, the differences become smaller, in relatively speaking. And I will show this to you in the next picture. This is for low order moments. See, it varies now with respect to this aspect ratio parameter. But if you go to high order moments, it is really not changing at all. And what it means is that the tails of the distribution somehow become universal. And in fact, the low order moments, which are coming from the bulk of the distribution, really are not universal. And that's a general idea that this picture is showing. And in fact, you can do this a little bit better or a little bit differently by using the theoretical fit, which is this here. And you obtain the circulation using the theoretical integral, and it gives an expression whose for large values of m and n, you can take the asymptotic form, and it gives you this formula, which basically the only thing I want to point out is that it does not depend on anything relating to the loop itself. M and n are simply the orders of the moment, which I've used here to normalize relative to each other, and it's completely independent of everything else. So it's independent of the loop area, prefactors alpha and beta in the PDF distribution, and only depend on the order of the moment. The tails of the PDF are universal, and this is the essence of the area rule. Okay, it's not that the whole distribution is universal, although to a reasonable approximation, it looks like that. But if you put it to real serious test, this is what you find. Now, what if you have the loop which is not simply connected, but not a simple square or circle, but as a figure-8 loop? So if I go for circulation around here, the area is to the left. Therefore, let's pretend that it is a positive sign. But if you go to this part, the area is to the right. Therefore, it will have a negative sign. So when I take the circulation around a contour like this, should I add these two circulations up algebraically, or should I just add them up arithmetically? So that's something that we can answer very easily. if the scalar rule works, that is, you add them up linearly, I mean arithmetically, then you get the variance going like a to the power 2/3, and if the vector area matters, then it will go like 1/3, area to the power 1/3. And this is very easy to check because that's such a huge difference in powers. And what you find is, in fact, if you take different loops like this, going an aspect ratio from 1 to 16, you see that data fall on each other very nicely, and 2/3 power is really what they follow. So in fact, what it means is that when you go to loops like that, you go only add them up arithmetically. What if the loop is not planar? You know, so far I'm only talking about squares, etc., but they are all in one plane in the flow. Now, suppose I have a thing like that, which is like a laptop, for instance, or what we call a soccer gate, or some other football gate, for instance, if you like. So if I have a surface that is sticking to the edges of these edges, now what will be the area rule for that? In fact, Sasha thought it would go like it would be related to the minimal area of the surface, which is like the I don't know. You probably know minimal area in many different contexts, but I will not talk about it. But like a soap film that sort of attaches to all the edges of these, and it has a certain area now. And how is the area related to the circulation in it? Just like we had done the previous case of a planar thing, we can ask for a 3D surface like that. And therefore, what we did was by tessellating this by different objects, you can compute what the area is, and you ask yourself whether the circulation or the statistical property circulation in this three-dimensional space, non-planar areas, would it be the same as that of a planar one with the same area? See, that's the essence of the area rule. Actually, that's not exactly true, is what we find. We find that non-planar and planar areas actually differ in probability densities here. If I plot just the probability density, bare probability density, but if I normalize it by the variance or something internal to the distribution, then in fact they seem to follow each other. This is for second order, this is for eighth order. So in fact, therefore, you might say that the area rule does hold, except that it has to be normalized by its own inner variable, internal variable, like the variance or something like that. So that's how far it has gone. Now I want to talk about what simplicity this brings in relation to the velocity differences. So recall that this is the normal scaling for the velocity differences. I used a slightly different symbol earlier, but never mind. And this is the Kolmogorov scaling. And the anomalous scaling is that this is not p-thirds, but it's zeta p not equal to p-thirds, and it is not linear. So if I find a solution for one p, it does not tell you what the solution is for other p's. So that's what we have. So we have to deal with the problem for infinite number of p's, infinite numbers of values of p. And let's do this exercise for the circulation. And say that circulation raised to the power p, the pth order moment, will go like r to the power lambda p, and take squares of different sizes r, and we find these exponents. So here is the various moments, 2, 4, 6, and 8. And if you had a power law with respect to r, that is the size of the contour, I'm using only the squares because pretty much the area rule works. And this is, instead of taking all kinds of shapes, I only take squares. And you can see that this may have pretty good linear regions in this log-log region. In fact, I do a little bit better by taking the local slopes as we did before. And for the second order, you see, it's in this region, which is the scaling region, it's pretty nearly constant. So the power law is very robust. You go to higher orders, it is not so robust, but it is still not so bad at all. And the lines that are drawn here are the Kolmogorov values. Okay, so what it says is for low order moments, they are Kolmogorov, but if you go to higher and higher order moments, they sort of depart from the Kolmogorov by increasing amounts, but not a vast amount. And this is what I will show here. So I plotted here P, that is the order of the moment, and this exponent here, and what the data are shown here. And if this Kolmogorov, it would be this red line, red dashed line, which is what the low order moments are saying. And at some point, it departs from the Kolmogorov in this fashion, but they appear on another linear curve. In fact, this is an expansion around some region here. So what this says is that instead of having a curve whose formula you do not have, and therefore you can't translate your knowledge from one order moment to another order moment, you have here the simplicity, essentially, that you have one linear relation, another linear relation here. And in fact, this departure changes with the Reynolds number. So presumably, this is the highest Reynolds number data we have, so I don't know whether it will continue to decrease as the Reynolds number goes up. But I know that as you decrease the Reynolds number, this difference increases. Essentially, therefore, what we would be saying is that if you go to higher and higher order moments, presumably this line will behave, will sort of be on the same line for higher and higher order moments, and you need even higher order moments in order to see the deviation from the Kolmogorov line. So essentially, I think if this is true, which we think it is, I think this is an extraordinary simplification for the problem that has infinite number of variables in the present formulation to two variables, and perhaps only one of them is important for you if you are interested in moments which do not exceed this number. So here is a summary. The universal form proposed by Kolmogorov does not work, but it continues to be inspirational. And scaling is much richer than a simple extension of the Kolmogorov formulation suggests. They are anomalous, which has been known for quite some time. I'm not the only one who worked on it. There were several others before me, after me, etc. And the fact that the saturate is new. The fact that the different components scale differently is new. And the fact that the pressure effects seem to vanish for higher orders is an extremely valuable statement which allows you to close the equations. And other people like Victor Yakot and my former student Susan Kurian, we worked on this, and now Victor and I are writing another paper on this. So it actually allows you to close the equations and get a lot of details. And circulation appears to be quite promising quantity. In particular, the area rule holds for the tails. Circulation seems to lie. Sorry? Are you saying something?
No, Srini.
This is my last thing anyway. It lies on a bifractal set. That means there's one fractal for low orders and a space filling fractal, that is. And for high orders, you have a non-space filling fractal and a very simple fractal, not a multifractal. And the question is, of course, for increasingly higher Reynolds number, will the circulation eventually become Kolmogorov-like? And of course, we have no idea whatsoever. The problem of exponents would then be resolved in a very simple way for circulation. Now, what the relationship between the circulation and the velocity differences, which have been the staple diet for the last 80 years or so, remains to be understood, and how to translate this simplicity, presumed simplicity, to many things that you would like to compute, I think will be the kinds of things to do. So I am very grateful to you for your patience, and I'm sorry we had initial trouble, and I'm happy to answer any questions there might be. Yeah, that's it.
All right. Well, thank you. Thank you, Professor Sreenivasan. That was a wonderful talk.
Thank you, Tim.
That was
If you
awesome.
say
Thank
so.
you.
Okay, all
So
right.
I think what we'll do is we're notionally supposed to be done at 4:45, but I certainly would like to stick around for questions. So why don't we, for those of you
4:45 it is.
we'll stay and if
4:45, in spite of the fact that we started late.
that's right. So if you're okay, if we'll run it for another 10 minutes or so and take questions.
I'm happy. Yeah, I'm happy to stay.
Why don't let's start with Prasoon Sashandra. If you want to unmute and ask your question, and if others have questions, if you can start entering them in the chat as well, but I'll let Prasoon go ahead.
Hello, Professor
I
Sreenivasan.
could stop sharing my screen, couldn't I? Then I can see him.
Yes.
Okay, let me stop sharing. Okay, sir. Now I can see you.
Hello.
Yeah.
Yeah. Hello, Professor Sreenivasan. Great talk, and yeah, we have been like following your work. So my question was like, so I'm a student in Professor Devesh Ranjan's lab, and like we work in like environments where like to start with our flow is like quite inhomogeneous and anisotropic, like
Yes. Yeah.
affected by related instability or Meskov instabilities. So how do you think? Of course, we don't have that big of a data set compared to what we have for grid turbulence and all for anisotropic flows. So how do you think, like, what is the future of such scaling analysis for like anisotropic flows?
Okay. Well, thank you for the question. Now, leaving Rayleigh-Taylor aside, let's take some other flow like boundary layers, for instance. In boundary layers, there is one plane, two-dimensional flow, where there is a homogeneity, and you can, of course, make all these property evaluations. What might be interesting there is to see how inhomogeneity and anisotropy will influence these properties. So I would say then it will add more richness to it, which is to say that what I have been doing is probably not going to be a big part of the story at all. So that is one answer to your question. The other answer is that technically turbulent flow, there are infinite number of them, and we probably will never understand all of them. Therefore, if we understand one flow very well, that is really seriously, then perhaps that will give us a lot of value to the work. So that is another part of the answer. I think both of them are valid for your purposes.
Thank you for your answer.
Yeah.
All right. Well, I'm going to take the chair's prerogative and ask the next question because I don't see any other questions in the chat. But if those of you do have a question, I guess I want to ask a question about, very high Reynolds number shear flows, where you have, the simultaneous presence of low dimensional, very large scale disturbances embedded in the flow at the same time. And, I was just thinking about some of the scaling that you talked about at the end and, some of the implications for extreme events and things like that.
Yeah.
How do things change or just, I guess, around some of those conclusions that you presented, in the first part of your talk?
Yeah. So the what if the scaling results hold? It simply has the same exponent, but they vary in strength with respect to the Reynolds number. If the scaling result is true, and I hope some of what I said they are actually true, then basically it just means that everything goes like a power law with respect to the Reynolds number. So you just asked a very important question. The large scales are relatively simple, let us say, and low dimensional, as you called it, which may or may not be true, but simply simpler. And as you transition somehow to this inertial range, that's when you have this multi-scaling behavior. And this multi-scaling behavior does not increase in complexity as you go in Reynolds number, but they become sharper and sharper as you go in Reynolds number, according to a known power law. That's the purpose and sense of power laws.
Thank you.
Tim, I have a, can I just?
Yeah, go for it. Yeah.
So I have two follow-on questions, Srini. One is on the first part of your talk. So the inherent assumption you have that the initial condition does not play a big role at the late time in the flow field. But for a lot of practical purposes, for let's say you're designing a combustor or industrial application, it's very hard to decouple that. So how do you see practical application applying some of these scalings, especially when they're designing or trying to use these relationships?
Yeah. The truth of the matter is, for many things, initial conditions do matter in turbulent flow. So in fact, there is not going to be one universal theory that will tell you, okay, if you understand this, everything else will follow. What I think is it's a little bit like quantum mechanics. You know, if you take one atom, like the hydrogen atom, you sort of know all of its properties. You really don't know how to compute a nitrogen atom. You will have to compute it from some approximate principles. So my own thinking is thinking of it in an abstract way, which is probably the sense in which you meant. Even if I solve the problem of homogeneous isotropic turbulence, solve in some very well understood way, I will not be able to tell you how the combustor turbulence would be like. You will have to solve it using Navier-Stokes equations, more complex ones, density changes, and all that kind of stuff. But I think at the bottom, you will know that there is a theory that must work in some general sense for turbulence as a whole. And for specifics, you will have to really solve a particular problem on its own merit. However, if you want to ask about how small scale structure, whose universality we discussed today, will vary with Reynolds number, there you might expect some level of independence from initial conditions. And you might ask, where is the will there be a hotspot of a certain amount? Then I think you can answer with some modest level of confidence. So you have to take it like that. It is a problem, only a part of which, or a small fraction of which, you can theoretically understand. The rest of it, we have infinite number of flows. I mean, we will never understand them all the way we want. It's a slightly pessimistic view, but I think a quite accurate view.
Or a job security view.
What's that?
A job security view for everyone on the phone here.
Well, you know, I mean, there are still people who worry about quantum mechanics, let's say it's the fundamental principles, and whether in fact the philosophy of quantum mechanics is correct and things like that. And so there will always be people who will worry about that kind of stuff, even if you solve one thing. But I have to say, if you take chemistry, for instance, we can calculate with relative ease many compounds or many gas molecule properties and so on, and there are electronic properties you can compute. I mean, you will be able to do that a lot better. You might say chemists are really indispensable. There is no simple solution to any problem in chemistry. You just have to have many chemists all the time. Like that, you'll need many fluid dynamicists all the time.
We have time for one more question.
Yeah, so I was going to just follow up on the Tim's question with the shear flow. For a high Reynolds number shear flow experiments, if you think about two different layers, which have very disparate viscosity, so maybe viscosity ratio of thousands, but has a large shear, and these flow streams are still very turbulent. Do you expect the phenomena for the high viscosity disparity to behave very similar if the Schmidt number is same, or do you see that to have a dependence on the viscosity ratios?
So, well, if the whole analysis is right, if I know what the Reynolds number scaling is, I know what the viscosity scaling is, as long as the theory holds for these two flows, you don't need to worry about the second flow if you know what the properties are for the first flow. And anything that I will say now will have to be particularly valid for small scales. And for large scales, like Tim was saying earlier, there's a whole lot of simplicity associated with that. And so together you can actually make a theory, I think. And that's the substance of this paper that Victor and I have been struggling with for years on end. But
yeah, I was going to ask you, do we ever gonna see a Reynolds number where we can say Reynolds number above X and it's a turbulent flow, irrespective of what that flow geometry is?
so you will have to ask what is fully developed turbulence, right? And the only thing we can say is that if you go from one Reynolds number to another, you don't have a new phenomenon appearing, but you have some scaling from one Reynolds number to another. And if that is true, then you only have to find out what the corrections are for finite Reynolds numbers and things like that. But other than that, as long as there is no new phenomenon, well, we are all set in my view. But I don't know. If you go to Reynolds number, which is 100,000 times larger, will you discover a new phenomenon in it? Our current thinking is no. As long as there are no other parameters in the flow like compressibility and density difference and things like that. As long as they are not there, we don't think there is any new phenomenon happening, but only things becoming smaller in some known way if we have a theory. I think that's all there is. I think that in itself is an extremely powerful statement, if it is true, which I think it is. But yeah.
All right, Devesh, I'll turn it over to you to close us out.
Yep. So I want to just take this opportunity and thank Srini for accepting the invite. I know it's Friday evening, but thank you very much, and Tim for moderating it. And just a reminder, next week at the same time, we will have two junior faculty members who are doing outstanding research talking about their work. So please do join at that point.
So I want to say thank you again to all of you for staying so late in the day, and also for putting up with my own idiosyncratic talk. Thank you so much.
Thank you, Professor. Good to see you.
Okay, bye.
We'll remember that pressure effects vanish, Srini. That was the emphasis.
That is a very important point. Yeah.